So today we are going to talk about a new chapter, chapter 8, which is friction. In this chapter, we are going to talk about characteristics of dry friction, and also we are going to solve problems including dry friction. But first, we need to understand the concept of dry friction. Because of dry friction, forces is going to be developed. We need to understand how those forces is going to develop, how to deal with the forces as a result of the dry friction. Then we are going to solve problems in equilibrium of particles, or the equilibrium of a rigid body, and we are going to involve the dry friction. So in order to understand the concept of dry friction, we need to understand the movement of a box on a rough surface. So here we have a box with a weight W here. Of course, the weight is going to be applied at the center of gravity of that box. Here we have a force P pulling the box here, and here we have rough surface. So in reality, if you have box like that and you have rough surface, if you are trying to pull the box with a force P, you have two options. Either the box is going to be as it is, which means that you apply a force which is not enough to be more than the forces here. The other option, you are going to apply a force, and as a result, the box is going to move in this direction. This means you apply a force more than the forces acting on the rough surface. So I have only after a specific amount of the force, the box or the crater will move. To understand what's going on here, we need to take a sample to know what is going on here, what preventing the box from moving in that direction. So we are going to take a sample here. We are going to magnify it like that. So we need to examine the contacting surface between the block and the floor. Then we are going to have that we are going to see irregularities here between the two surfaces. So between that surface here, between the block and the floor, we have irregularities like that. So when you are pulling the box, you are going to have reaction, and at each point of contact. So if I'm going to have contact here, I'm going to have reaction, and here and there. So I'm going to have reactive forces at each point of contact. So when you are pulling the box here, I'm going to have a reactive force at each point of contact. And those forces, it could be dissolved into X and into Y. The forces into Y-axis represent the normal force, the reaction in Y-axis. The forces, the component of the reactive forces in X represent the frictional force. So I'm going to decompose the reactive force. I'm going to have normal force, and I'm going to have frictional force. Then I can use the summation of the forces in X-axis. I'm going to have F1, F2, F3, F4. I'm going to have FR, the frictional force. So here at each point I have frictional force. I'm going to get the summation of that frictional forces. I'm going to end up with FR in that direction. And the direction of the frictional forces is going to be opposite to the applied force. So if its P was that in that direction, then the friction is going to be in the opposite direction. And like you can see here, the value of the normal force here is not like there, is not like there. So I'm not going to have normally distributed forces. The forces is going to be different at each point. So I'm going to have something like that. So if in order to get the resultant force for this here, the resultant is not going to be at in the middle, because the resultant force is going to be applied at the center of gravity. And since here the distributed force is not normal, it's not equal at each point, in that case the point of application is going to be random. We are going to assume the point of application is O. And in order to know the summation of that forces, I need to get the reaction, I need to get the integration for that area here. So in order to get the resultant force, or the normal force in this case, I need to apply the integration in order to get the force. So here he says that the value of n is not in the center. Why? We answered that question. Finally, we can draw a free body diagram for the box case. Here we apply a force F, and the box, it has a weight. The weight is going to act down in this direction, and is going to the line of action is going to pass through the center of gravity of the box. And instead of the contact between the floor and the box, we are going to have frictional force opposite to the applied force, and we are going to have normal force here in order to encounter the weight of the box. So now we understand how the dry friction is going to be expressed in terms of forces. So we are going to have frictional forces, and we are going to have normal forces. Then we have the tipping effect. The tipping effect means that sometimes when you apply a force to a box, we are not going to have sliding, which means that if I'm going to apply that force here, sometimes we are not going to have sliding. The box is not going to move in that direction. The box is going to turn over. The box is going to turn over. We call this tipping effect. And the tipping effect depends on the value of h here. If you are going to increase the value of h, that means the possibility of tipping is going to increase as well. So for the tipping to take place, that means that force is going to cause a moment more than the moment that it can be caused by the normal force. So we need to apply equations of equilibrium in order to understand this. So since the box now is in equilibrium, I can say that summation of the forces in x-axis should equal 0. I'm going to have P positive and F is negative. It means that the applied force here equal the friction force. And also, if I'm going to apply the summation of the forces in y-axis, I'm going to have the N, the normal force, and the W, according to the sign convention. This one is positive, this one is negative. So N equal W. So in order to have equilibrium, the value of the P should equal the value of the frictional forces. In that case, sliding will not going to take place. Also, in order to know whether turning over is going to take place or not, we are going to take a moment at the point O. So if I'm going to take the moment about point O, then F is going to be cancelled and N is going to be cancelled. Only W and P is going to cause a moment. So I'm going to take the moment here. The value of P is going to cause a moment because of that height. If I'm going to draw the line of action here, here is the perpendicular distance. And W here, if I'm going to draw the line of action, is going to multiply by the distance x here. X represent the perpendicular distance. So W times x is going to cause positive moment, Wx, and PH times h is going to cause a negative moment. So if these forces are equal, then the moment is not going, the turning over is not going to take place. So we need to know the value of x. Here is the value of x. If the width of the box is a, so the distance from here to here is a. If the value of x came out to be more than a over 2, that means tipping will take place, turning over will take place. If the value of x is less than a over 2, then the turning over will not going to take place. So in order to understand the tipping effect, I need to take a moment about the point O, and then I need to know the distance where the normal forces is located. If it's located within that region, that means the turning over will not going to take place. If it's more than that region, that means the tipping will going to take place. Also, to understand the mechanism of the dry friction, we are going to see the relation of the P and F. So again, if I'm going to have a box here, I have the value of the, I have the applied force. Assume that I'm going to apply that force slowly. 1 kilonewtons, 2, 3, 4, and so on. Then in x-axis, I'm going to have the P, the applied force, and in y-axis, I'm going to have the frictional force. When I apply that force here, what will happen to the frictional force is going to increase as well. When I increase the applied force, the frictional force is going to increase. And we know that the frictional force is going to be tangent to the contact surface here. So when I increase the value of P, the value of the frictional force is going to increase as well, like that, until we get to a point where the frictional value here is going to reach its max value. After that value, the box is going to move, is going to slide after that value. That value is Fs, which is the maximum static frictional force. So when the frictional force reaches that value, that means the box is about to slide. Then instead of the static frictional force, we are going to have kinetic frictional force. So at that point here, when I reach that point, if I'm going to draw a line here, I'm going to have motionless. The box is going to be stable. After that value, we are going to have motion, kinetic. So if the force now more than the frictional, the static frictional force, then the box is going to move. And now we are going to have a resistant, but that resistant is the kinetic resistance, which means that I'm going to have frictional resistance, but the box is going to move. And the force of the kinetic frictional resistance is slightly less than the static frictional force. So how I'm going to know the value of the static frictional force? They have done many experiments in order to know the value of Fs. So experimentally, the value of Fs came out to be μs times n. N is the normal force. So we have a proportional relation between the value of Fs and the value of the normal force. Μn is the coefficient of static friction. It depends on the surface here. Depends on the depends on the material here and the material there. In order to know that value, we have a table. It has been designed in order to know the value of μs, and that it has been proved experimentally. When the box is on the move, then we are going to have the kinetic frictional force, and that equal, instead of μs, we have μk, which is the coefficient of kinetic friction. Also, we have a table for that. The value it has been obtained experimentally. So to summarize all of this, the characteristic of dry friction: the frictional force acts tangent to the contacting surfaces. So here is the contacting surfaces. The value is going to be tangent to that surface, and it should be opposite to the applied force. So if the tendency of the force in that direction, the friction is going to be opposite to the tendency for motion. And if the box is not moving, we can apply the equations of equilibrium. So if the box is not moving, we are in a position to apply equations of equilibrium. Then when slipping at the surface of the contact is about to occur, when we are going to have a slipping, which means that the box is going to move in that direction. In that case, the static frictional force is going to be maximum, and we are going to call it Fs. And Fs equal μs times n. N is the normal force, and μs is the coefficient of static friction. When slipping at the surface is occurring, when we are going to have motion in that direction, in that case, the frictional force is going to be kinetic frictional force, and it's proportional to the normal force, like you can see here in the equation, and we have the coefficient of kinetic frictional force. So in order to connect all the concepts together, it's important to solve example so that we can connect all the information that I have mentioned here. So let's start with example 1. In example 1, we have a box here, and the load here is uniform, which means that the resultant force or the weight is going to act at the middle here, center of gravity. So we have uniform crate shown in this figure here, and the mass of that crate or that box is 20 kilogram. So we need to multiply by 9.81 in order to convert it to Newton. Then we apply a force P with angle 30 with x-axis, and we need to know if that box is going to maintain its equilibrium or not. So I have a box here, I have a service, and I have rough service, and the static friction for that service here is 0.3. So they gave us the coefficient of static friction, and we apply a force here. They want to know whether that force P is going to cause movement or not. Before that, we need to understand how the box is going to be unstable. So in option 1, I'm going to apply that force, and we are not going to see any movement. In that case, the box is stable. So the box is in equilibrium, even though I apply that force. That means the frictional forces is more than the applied force. Other option, when I'm going to apply that force here, the box is going to slide. It's going to move like that. So the box is going to move from here to here. And we are going to call this sliding. The third option is that the box is going to turn over. It's going to tip. We call this tipping. So we want to know that whether the box is going to be stable or we are going to have sliding or tipping. Sliding means that the box is not stable. Tipping also, it means the box is not stable. But also we want to know which type of instability we are going to have, or either to have sliding or tipping. So in order to deal with that problem, we need to draw the free body diagram. So here we have the box. We need to draw the free body diagram. Instead of the friction here between that surface and that surface, we need to put the forces acting on the box. So like we learned, instead of the surface, we are going to have frictional forces and normal forces. The frictional forces is going to be opposite to the tendency of motion. So if I apply force here, I'm going to expect that the box is going to move into that direction. So the frictional force is going to be opposite to that direction. And we have normal force, and we don't know the location of the normal force here, because the normal force is going to resist the tendency of that box to turn over. So the value of the normal force is going to be applied at distance x from the center of gravity of the box. And here we have the weight of the box. We convert the value to weight here, and the line of action is going to pass through the center of gravity of the box. So now we draw the free body diagram. Then we need to determine the number of unknowns and compare it with the available equation. We are going to use the equations of equilibrium, which means that we are going to have 3 equations. And here we need to know the unknowns. We have the frictional force, we don't know. We have the normal force, we don't know as well. And the distance x, also we don't know the distance x. So we have 3 unknowns. And we have 3 equations. In that case, I'm able to solve the unknowns because I have 3 unknowns and I have 3 equations. So now I'm going to apply the equations of equilibrium. So I have at most 3 unknowns. I'm going to start with the first equation. So the summation of the forces in x-axis should equal 0. In order to do that, I need to decompose that force into x and into y. Into x is going to be 80 times cosine 30. Into y is going to be 80 times sine 30. And in x, according to the sign convention, that force is going to be positive and the frictional force is going to be negative. So here we are going to have 80 cosine 30, and here we have minus f, the frictional force, equal 0. Now I have one equation, one unknown. I can easily know the value of the friction. So when I apply that force, I'm going to have friction equal 69.3 newtons. Then I can also apply the summation of the forces on y-axis here. And don't forget here I have component into y acting down equals 80 sine 30. So I have the component of that force acting down, and I have the weight of the box, and I have the normal force acting up. So positive, negative, and negative. I have minus 80 sine 30, the component in that direction. I have plus n, the normal force, and this value here, the weight, is minus. So again, I have one unknown, one equation I can easily solve for NC. NC came out to be 236.2 newtons. So now I know the value of F and I know the value of N. Now I need to know the value of X. In order to know the value of X, I'm going to use the summation about the point O here. So I'm going to take moment about the point O here, take care of the sign convention. So the value of F is going to be cancelled. The value of the weight also is going to be cancelled as well. I'm going to have component here and component there. They are going to cause a moment. So the component into X is going to be multiplied by 0.2. The component into Y is going to be multiplied by 0.4. And here NC is going to be multiplied by X. NC times X is going to cause positive moment. The component into Y is going to cause positive moment as well. The component into X is going to cause a negative moment. So we have positive moment from Y times 0.4. We have negative moment as a result of the component into X. Here is going to be multiplied by 0.2, and the NC is going to cause positive moment. Here I have one unknown, which is X. I already determined the value of NC. So now I determined the value of X. It came out to be negative. If the value here is negative, that means the value of X is left to the center of gravity. So the value of X really is here, not there. So that means the value of X is left to the crater's center line. And the value of X came out to be minus 0.00908 meter. And remember, for tipping to take place, the value of X should be more than that value, A over 2, which is 0.4. The value of X is less than 0.4. That means tipping is not going to place. The box is not going to turn over. And for the friction, that value here, it should be more than the maximum value, which is Fs. So also we are going to determine the value of Fs to compare it with the value of F here. If this value came out to be more than Fs, that means sliding is going to take place. So no tipping will occur since x is less than 0.4 meters. And also the crater will not slip because the value here is less than the maximum value. Remember, at the maximum value, the box is about to slip. Since the frictional forces here is less than the maximum static frictional force, it means the box is not going to slide. So here in this example, we are not going to have sliding or tipping. It means that the box is going to be in equilibrium, even though we apply that force. Okay, so the answer to that question, the box is going to remain in equilibrium. No movement is going to take place in this example. So 2. We solve example 1. In example 1, they give us the value of the P. And it's required to know whether the box is going to be in equilibrium or not. This time, we don't know the value of P. We need to know the value of P that will cause the box to move, whether it's sliding or tipping. So in this example, we have that box. The height is 2 meters and the width is 1 meter. And the weight of that box is 200 newtons. And the coefficient of friction is 0.3. And the question says, determine the force P needed to cause impending motion of the block. So we need to know the value P, the minimum force that will cause the box here to move. And then we need to know the type of movement, whether it's slipping or tipping. So we are going to first understand the motion itself. So first, the value of B will not cause anything. So in that case, the box is stable. And if I'm going to increase the value of P, then the box is going to be unstable. And that could be by sliding. That box is going to move from that point to that point, or by tipping. The box is going to turn over. So we need to know the minimum value that is going to cause slipping or tipping. We don't know which one is going to occur first. So in order to solve the example, the first step needs to be done. We need to draw the free body diagram. So the weight is going to be applied at the center of gravity for that box, and the contact surface here, we are going to have frictional force opposite the value of V, and we are going to have normal force. It's very important here, the value of the frictional force is going to be opposite to the value of P here. So here is the value of P, and the frictional force is opposite to that one, and we are going to have normal force at distance x here. The x here is very important in order to resist the moment. If the value of x came out to be more than that value here, which is 0.5, that means we are going to have tipping. If the value of P here is more than the value of the frictional force, then we are going to have sliding. So now we draw the free body diagram. We have the force P, we have the weight acting down, we have the normal force acting up at distance x, and we are going to have the frictional force opposite to the applied force P. Now we need to determine the number of unknowns in this problem. In this problem, we don't know the value of P, we don't know the value of F, we don't know the value of N, and we don't know the value of X. So in this problem, we have 4 unknowns. We have P, we have F, we have N, and we have X. And how many equations do we have? We have 3 equations. We have the moment about any point should equal 0. We have the summation of the forces in X should equal 0. And we have the summation of the forces in Y-axis should equal 0. So in this case, I need to do something so that I can determine the unknowns, because I have 4 unknowns. So in this case, I need to assume. I'm going to assume that the surface here, the slipping, is about to occur. So I'm going to assume that the box is going to slide, is about to slide. So if the box is about to slide, it means the value of F is the maximum static frictional force, the Fs. So in that case, if I'm going to assume that the box is about to slide, that means the value of the F is going to be known for me, which is the Fs, the µs time n, the normal force. So first I need to know the value of n. The value of the coefficient is given, which is in the beginning here. The value is 0.3. The value is given. So I need to know the value of the n, the normal force. In order to know the value of n, I need to apply the equation of equilibrium, which is summation of the forces in y-axis should equal 0. So here we are going to assume that the box is about to move, is about to slide, then F equal Fs. So in order to know the value of n, if I'm going to say that summation of the forces in y-axis should equal 0, that means the value of n is equal 200 newtons. So I can know the value of the friction frictional force. It's going to equal 0.3 here µs, and the value of n is 200 newtons. The value came out to be 90 newtons. Then I'm going to take the moment about point O. But before that, if I'm going to apply that formula, the summation of the forces in x-axis should equal 0. That means the value of P is going to be 60 newtons. So if the box is about to slide, then the value of S is going to be Fs. And I can calculate the value of Fs. Then, in order to know the value of P, I'm going to use that formula here. The summation of the forces in x-axis should equal 0. According to the sign convention, this one is positive and this one is negative. I can easily determine the value of P. P came out to be 60 newtons. This is the value of P. Here I assume that slide is going to take place. What about tipping? So now I need to know the value of X to know that whether the tipping took place or not. Because if I'm going to take the moment here and the value of S came out to be more than 0.5 meter, it means that the tipping took place before the sliding. Because we assume that the box is about to slide. It's about to slide. So if the value of X came out to be more than 0.5 meter, it means that tipping took place before sliding. So to make sure that we don't have any tipping, we need to determine the value of X. So we are going to take the moment about the point O. So 200 is going to be cancelled, F is going to be cancelled. I only have the P and the N. The P is going to cause a moment. negative moment, and here is a perpendicular distance 2 meters, and n is going to cause positive moment, and the perpendicular distance is x. So n is going to be multiplied by x here, the perpendicular distance, and the p, which is 60, is going to be multiplied by the perpendicular distance, which is 2. Now I'm in position in order to determine the value of x. The value of x came out to be 0.6 meter. So in order to have a balance, the value of n should be here, which is more than 0.5. That means the tipping already took place. So it's mean that my assumption here is wrong. My assumption here is wrong. I assume that the failure is going to be due to sliding, which is wrong here. Because when I assume that we have sliding, the value of x came out to be more than 0.5. That means tipping took place before the sliding. So in this problem, now we know that tipping is going to take place before sliding. And for the tipping, for the tipping to take place, the value of x should be 0.5. So I'm going to cancel all of this here. I'm going to assume that the value of x is going to be 0.5, which means that the box is about to turn over. Then I'm going to take the moment about the point O. Now I don't know the value of P. Here, yes, I assume the sliding, and I get a value of P. Now I'm going to cancel all of this. Okay. Then I'm going to take the moment here. The value of n, I know the value of n is going to be multiplied by 0.5, because here is the critical distance, and here we have the P time 2 equal 0. I can solve for P. So P came out to be 50 newtons. So P, 50 newtons, is the critical applied force. If I'm going to apply 50 kilonewtons, then tipping will take place. And the sliding is not going to take place, because now if I'm going to use that formula here, the value of P, 50, less than the maximum frictional force. So in this problem, in order to have motion, we are going to apply 50 newtons, and that is going to cause tipping, not sliding. Okay, I'm going to stop here. Now we are going to solve example 3. So in example 3, we have a ladder from point A to point B, and the weight of that ladder is 10 kilograms. And the weight is going to act, like we said, at the center of gravity, which is the middle of the ladder here. And we need to multiply by 9.81 to convert it to a weight. Here we have a mass. And we have a point of contact at B and point of contact at A. They say that the point of contact at B is smooth. The wall here is smooth. It means that we are not going to have any friction. So that point is going to move freely without any resistance. We are not going to have friction here. We are going to have only reaction because of that surface. So here, tangent to the surface, we are not going to have friction, or the friction is going to be 0. At the point A here, they said that we are going to have rough horizontal plane. So the plane here is rough, which means that I'm going to have friction and I'm going to have normal force. And they give us the coefficient of static friction, which is 0.3. So I'm going to have friction here. The static friction is 0.3. So I expect that the ladder is going to move in this direction and this one into that direction. So if I'm going to have a load here, the ladder, this point is going to move here, and that point is going to move here. So here is the direction of the movement. That means the direction of the friction is going to be opposite here. Here we are not going to have any friction. So the question is determine the angle of inclination, the angle theta of the ladder, and the normal reaction at B. Here we have normal reaction is going to be perpendicular to the surface if the ladder on the verge of slipping. Here it means that the ladder is going to slip. So we need to know the angle when the ladder is going to slip, which means that that point is going to move. So in order to solve that question, first we need to determine the free body diagram. Regarding the weight of the ladder, we are going to put 10, the mass, times 9.81, and the point of obligation is going to be at the middle of the ladder. And here at the point B, they said that the surface here is smooth, which means that we don't have any friction. We have only a normal force perpendicular to the surface, which is NB. And here at point A, we have NA, normal force perpendicular to point A, and here we have frictional force, FA. The direction is to the right because the motion is going to be to the left. And here we have the distance for meter. The length of the ladder is 4 meters here. That means the distance here is going to be 4 cosine theta, and here the distance is going to be 4 sine theta. So if this one here is 4 cosine theta, that means the distance from here is going to be 2 cosine theta, and this one is 2 cosine theta as well. The summation is 4 cosine theta. So the distance from here to here is 4 cosine theta, and the distance from here to here is 4 sine theta. Now we draw the free body diagram. Again, before we are going to move the equations, are going to use the equations of equilibrium, we need to know the numbers of unknowns. We have the theta, we have FA, we have NA, and we have NB. We have 4 unknowns. I cannot solve for 4 unknowns because I have 3 equations of equilibrium. So I need to do something about that. In the question, they say that the ladder is on the verge of slipping. So here they say that the ladder is on the verge of slipping. That means here the friction is going to be maximum. And if the friction is going to be maximum, that means the value here of FA is Fs. And Fs is the coefficient of the frictional force, and the value of N is the NA. So like I said, we have 4 unknowns. I need to do something about it. And here from the problem, we can know the value of FA. So the value of FA is going to be the mu s in A. The value of mu s is given, and I need to know the value of NA. So in order to know the value of NA, I can apply the that equation here. Summation of the forces in y-axis should equal 0. I have only NA, and I have the weight of the ladder. So I have only this one and that one. This one is going to be positive, this one is going to be negative. Then the value of FNA is going to be 98.1 newtons. So now I know the value of NA. I can determine the value of FA. Why again? Because we say that that point is about to slide. If that point is about to slide, it means the frictional force is maximum, and that represent Fs. So Fs is the Fa in that case. So I can determine the value of Fa. Now I know the value of Na. Fa came out to be 29.43 newtons. Then I can determine the value of NB by applying the summation of the forces in x-axis should equal 0. This one is going to be positive, this one is going to be negative. We already know the value of Fa. It means that I can know the value of NB. NB came out to be the same as Fa. Now the question is we need to determine the value of the angle theta here. So in order to do that, we need to take the moment about a point where I can determine the value of theta. So for example, if I'm going to take the moment about point A, I'm going to have that force times that distance and that force times that distance. In that case, the only unknown is going to be theta, the angle here. So I'm going to take the moment about the point A. The Fa is going to be cancelled, Na is going to be cancelled. I'm going to have the weight, which is positive, times 2 meter cosine theta. And here I have the weight is going to cause negative moment because it's clockwise. And Na is going to cause a positive moment because the rotation is going to be counterclockwise. And if I'm going to draw the line of action, for sine theta is the perpendicular distance. So this one is going to cause positive moment, and this one is going to cause negative moment. Here I have only one unknown, which is theta. If I'm going to simplify that problem, I'm going to find out that sine theta over cosine theta came out to be 1.667. Sine theta over cosine theta is tan theta. Then in order to know theta, I need to get the tan inverse of that value. And theta came out to be 59 degrees. So when that ladder is about to move, the angle theta here is 95 degrees. And this is the end of that example. If you are going to have any questions, please ask me